All right. So today we're going to learn about zero powers, negative exponents, even and odd, and undefined exponents. So first up, we're going to learn about negative exponents. So negative exponents, they are negative, but it does not mean the number is negative. They're kind of an interesting little convention. So when you see a negative exponent, it means reciprocal. And the F of flip dropped out, so you have to put the F's in there. Flip the number, and then after you flip the number, that negative exponent becomes positive. So it's only negative until you flip the number, and then it goes to positive. A negative number is not the same as, a negative exponent is not the same as a negative number. Those two things are completely different. So when you are simplifying an exponent, you can have no negative exponents in your final answer. You have to do the reciprocals and get rid of the negative exponents. You can have a negative number as an answer, just not a negative exponent. Adding, subtracting, multiplying, and dividing negative exponents, you do that first. And then once you've done all those operations and everything's as simplified as it can get, then you actually take care of the negative exponent second. So you eliminate the negative exponent last in your process. Okay, so we're going to do some examples, starting really simple and going more complicated. So example 1 is a to the negative n. The n is negative. So what it means is you're going to flip it. It's going to become 1 over a. And then now that you've moved it, it's going to be to the positive n. Because you've done the reciprocal. That was the only reason the negative exponent was there, was to tell you you need to find the reciprocal. So once you flipped it, it's gone. That's just a positive n now. Here's another one. 1 over x to the negative 2. So you're going to flip it. That means the x squared goes to the top, the 2 becomes positive, and you just have x squared. So bottom goes to top, top goes to bottom. All right, example 3. On this one, 4 and x are not to the negative 2, just the y. So the 4 and the x are going to stay on the top, and just the y squared goes to the bottom, and the 2 becomes positive after you've moved it. Okay, let's look at example 4. Now this one's different than example 3. This one has everything in parentheses and not just like one number. So I'm going to actually show you 2 ways to do this. You can pick which one you like the best. Okay, so the first way to do this is to distribute the negative 2. Remember that 3 has an invisible power of 1. So when you distribute, you're going to keep the base and multiply. So that would be 3 to the 1 times negative 2, which is negative 2. X to the 2 times negative 2, so that's negative 4. Y to the 4 times negative 2, so that's negative 8. So we got rid of the parentheses first. Now we're going to get, and that's as simplified as we can get using exponent rules. Now we're going to move all of the numbers with negative exponents by flipping them. So you're going to have 1 over 3 to the positive 2, x to the positive 4, y to the positive 8. And of course, if you're simplifying, the very last thing you do is multiply out 3 squared. 3 times 3 is 9. So 1 over 9, x to the 4th, y to the 8. So that's the first way you can do this. The second way you can do this is because the entire expression is in parentheses, you can flip it at the beginning and make it 1 over, and then parentheses, 3x squared, y to the 4th, quantity squared. Now that you've flipped it, that exponent 2 is positive, and then distribute it, which will put you right at that step. So both of these are good ways to go about doing it. You pick the way that makes the most sense to you. All right, let's do example 5. Power to a power rule says keep the base, multiply the powers. So this is x to the negative 2 times 0. Negative 2 times 0 is 0. And that's why you simplify before you start moving negative exponents around, because like on this one, the negative exponent went away. So you have to do everything else first and save the negative exponents for the end. Like we talked about yesterday, anything to the 0 power is a 1. And just as a secondary example out here, no matter what, you could have AB, quantity to the 0 power, and it would still be 1. Anything to the 0 power is 1. All right, example 6. Again, I'm going to show you 2 ways to do this. You can pick the way that floats your boat. All right, so when you have a fraction raised to a power of negative 2, that 4 is to the power of 1, 3 is to the power of 1. One way to do that is to take care of the negative by flipping the fraction. So I can flip it and make it 3 over 4 to the power of positive 2. So you can flip it at the beginning. Now we're going to use our power to a power rule on the top and on the bottom. So on the top, this is 3 to the 1 times 2. On the bottom, it's 4 to the 1 times 2. That's where we get 3 squared over 4 squared, which is 9 over 16. That's one way to do it, is to flip the fraction, make the exponent positive, and then distribute the exponent. The other way to do it is to distribute the negative exponent first. So you're going to multiply the 1 by negative 2 and the 3 by negative 2. That would give you 4 to the negative 2 over 3 to the negative 2. And then move the negative. So the top goes to the bottom, that's 4 squared. The bottom goes to the top, that's 3 squared. And then you're right here in the process. So whether you flip the fraction or distribute is up to you. Both of them will work. All right, flip the page. All right, Roman numeral 2, undefined numbers. Okay, what is undefined? Undefined means there's no possible answer. The abbreviation for undefined is UD, capital U, capital D. An undefined answer is not the same thing as a 0. A 0 is 0. 0 is a legitimate number. That is not undefined. That's just a 0. So the most of the time when it happens in our math for what we're doing, the 0 will end up in the denominator, and you'll have something like a number over 0, and then that will be undefined. You cannot divide by 0. Okay, so using this, we have an expression 1 over a minus 4. And we are going to evaluate, which means get a value or get a number for a equals 1 and a equals 4. So for a equals 1, I'm going to substitute 1 into the expression. That gives me 1 over 1 minus 4, which is 1 over negative 3. And of course, we never, ever, ever leave a negative monomial in the bottom. So the invisible positive divided by a negative is a negative. Move it to the top. We get negative 1/3. Okay, so that's evaluated using a equals 1. Now we're going to evaluate using a equals 4. So for a equals 4, it's going to be 1 over 4 minus 4, which is 1 over 0. We cannot divide by 0, so this answer would be undefined. So expressions can be defined for some values of a and not defined for other values of a. And that goes for any kind of a fraction that has a variable on the bottom of it. Variable on the top, never going to be undefined. It might be 0, but it's not going to be undefined. It's the variable on the bottom. So when you're looking for undefined values, you're looking here. You're looking at the bottom of it. All right, Roman numeral 3, even and odd powers. Here's the rule. If a negative number is raised to, number 1, an even power, so this is even, the result is always positive. If it is raised to an odd power, the result is always negative. All right, so let's do some examples of that. I have negative 3 to the power of 7. So if I don't know this rule, I'm going to have a rather long process because I have to write 7 3s next to each other. 1, 2, 3, 4, 5, 6, 7. And then aside from figuring out what all that multiplies together to be, I have to figure out the signs on it. But this is why this rule works. For every 2 negatives, a negative times a negative is a positive. So for those 2, I get a positive. For those 2, I get a positive. For those 2, I get a positive. And then I've got this last one here that gives me a negative. A positive times a positive times a positive is a positive, but a positive times a negative is a negative. So that one lonely negative makes my number negative. This is why we like having a rule, because that's time consuming. It's much easier to go, okay, I have a negative number to an odd power. That means the result will be negative. And I do not have to calculate out those negatives. I just do the 3 to the 7th. Okay, so now let's do a second one. This is negative 4 to the 4th. Let's pretend we don't know our rule. So you'd write out 4 negative 4s. And for every 2 negatives, a negative times a negative is a positive. So I get a positive for the first 2, a positive for the second 2, and a positive times a positive is a positive. I would get 4 to the power of 4 with no negative on it. Now again, that's time consuming. If you remember that a negative number to an even power means all of your negatives have a partner. If all your negatives have a partner, they're all going to multiply to be positive. Your answer is positive. So I think about it as even means everyone has a partner. People with partners are happy, they're positive. All right, let's do this last one. This one has a negative x, not a number, but that doesn't make a difference. We're going to use the shortcut. This is a negative number to an odd power. Any negative number to an odd power is negative, so it's negative x to the 9th, no parentheses. Right, flip the page. All right, graphing exponential functions. So your exponential formula is y equals a times b to the power of x. In this expression, a is what we call the initial value, which happens at x equals 0. So a is what you start with at x equals 0. Now there's 2 ways that an exponential can go. The first way is if the b, which is the base of the exponent, is greater than 1, then this is called exponential growth. So as x gets bigger, as x increases, y increases. Sometimes you'll see me write this as x goes up, y goes up. The other type of exponential function we have is if the b, the base, is less than 1, then it is called exponential decay, which means as x increases, y decreases. It gets smaller. And again, I oftentimes show this as x goes up, y goes down. Both types, growth and decay, have a horizontal asymptote at y equals 0. Both of them do. And if you remember from what we've done before, an asymptote is an invisible line that the graph gets infinitely close to, but it never crosses it. So we sometimes refer to asymptotes as guidelines because the graph guides closer and closer to that line. All right, so knowing that, we are going to graph y equals 4x. Now, the minute you see that this is an exponential function, and you can tell it's exponential because the x is in the power position. If x is just in front of the number, it's not exponential, it's a line. But this is in the power position. So you know that you have an asymptote, which you show using dashed lines and arrowheads at y equals 0. You need to draw that using dashes and arrowheads and label it y equals 0, either at the far right or the far left of the line. You don't put it like in the middle of the line. All right, we are going to graph this equation. I want you to make an extended H chart. So in general, when you graph an exponential growth or decay function, you want to find the initial value at x equals 0. And in general, you want to go 1 or 2 spaces right, 1 or 2 spaces left. Your guide is how big do the numbers get. If it gets super big, you can't graph those reasonably. So let's try 1 and then 2 to the right, and then we'll go -1 and -2 to the left. And if any of them get huge, we don't use them. Okay, let's start with the 0. Replace x with 0. So we get y equals 4 to the power of 0. Well, anything to the power of 0 is 1. So let's put a mark there. And on your graph, go ahead and label 1, 2, 3, 4, 5, 6, 7. This is growth, so it's going to go up, not down, so you don't have to worry about going down with the numbers. And then number to the right, 1, 2, 3, 4. Number to the left, -1, -2, -3, -4. Very rarely does it get up anywhere past 4s or 5s. Otherwise, the numbers get ginormous. All right, let's try the 1. Fill in 1 for x. We get y equals 4 to the 1. And 4 to the 1 is just a 4. So at 1, 4, make a dot. Let's try 2. Y equals 4 to the power of 2. 4 to the power of 2 means you have 4 times 4. 2 4s multiplied together, which is 16. That one's heckin' gone from our graph, so we're not going to use that one. Okay, now we're going to do -1. 4 to the -1. That's a negative exponent, so flip it. You get 1 over 4 to the positive 1, which is just 1/4. Now, these numbers get really small really fast, so you have to approximate the position of 1/4. Okay, let's do -2. So 4 to the power of -2 is 1 over 4 squared. 4 times 4 is 16, so 1/16. So this one is super close, just not crossing that line. All right, so we're going to draw the curve. It should be a curve. There shouldn't be any pointy parts on it. And what you do is you go right along your asymptote, and then you curve, and then it curves, and it gets steeper and steeper. And on the left, I always suggest people fill in the arrowhead so it's clear it's not crossing, because those numbers get really tight in that graph. Exponential growth curves, the higher the base, the sharper the bend. So if the base is like a 2, that curve would curve a lot slower. It would come out here and then climb up. The higher the base, the harder the bend. All right, so that is exponential growth. Let's label that. Exponential growth, which means as x gets bigger, y gets bigger. Bacteria is a good example of exponential growth. It duplicates and duplicates and duplicates and duplicates, and it grows super, super fast. All right, let's do the second one. This is y equals 1/2 to the power of x. So right away, you notice this is an exponential graph. So draw in your asymptote, dashed lines, arrows. I'd label it at the left if I were you, y equals 0. All right, let's make our extended H chart. Okay, so you always want your initial value, which is x equals 0, and we're going to do the same thing. We're going to go 1 and 2 to the right, -1, -2 to the left. So let's start with the x equals 0. So we have 1/2 to the power of 0. Well, anything to the power of 0 is 1. So go ahead and mark 1, 2, 3, 4, 5 up. 1, 2, 3, 4 to the right. -1, -2, -3, -4 to the left. If you label your axes, you don't have to label the specific points. All right, let's do the next x. X equals 1. So I have 1/2 to the power of 1, which is just 1/2. So at 1 to the right, we're going to go up to 1/2. Make a dot. Okay, now 2. 1/2 to the power of 2. Power of 2 means 1/2 times 1/2, which is 1/4. 2 to the right, 1/4. We don't need to go any further than that. We're already right up against our asymptote. So now we're going to go to the left and see how curvy this is or how bent it is. So let's do the -1. So 1/2 to the power of -1. This is one where it's easier if you flip the inside rather than distribute. So it's 1/2 to the 1. So the inside gets flipped, 2 over 1, and the power becomes +1, which means the 2 over 1 is just 2 over 1, which is 2. So -1 up 2. And our last one, 1/2 to the -2. Let's flip the fraction. You get 2 over 1 to the +2. Now remember that the 2 and the 1 both have invisible ones. So power to a power means we multiply. So I have 2 to the 1 times 2 over 1 to the 1 times 2, which is 2 squared over 1 squared. And 1 times 1 is just 1, so we can disregard that. 2 times 2 is 4. So -2 up 4. So this is decay. You could tell because the base of the exponent was a fraction. So it's going to come down, and then it's going to get really flat, but never cross the asymptote. Draw in your arrows. Now, if you compare that to the other curve that we did, you can see the other curve has a sharper bend. That's because 4 is a lot bigger than 1/2. The higher the base, the sharper the curve. All right, do we have any questions?